Okay, hope everybody had a good day today. We're going to begin week number 4, and today's topic is going to be the current divider. The current divider, up until this point, we have studied both series combined circuits and parallel combined circuits. So as a prelude to getting into the current divider and ultimately the current divider formula, we're going to do a very short review to differentiate between the two different types of connections that we've studied so far. The first kind obviously is series. We've seen better days here. Series connected circuits are circuits that are connected in a cascade configuration or connected end to end. And as a result, if this were resistor 1, this were resistor 2, this were resistor 3, the current would be forced to flow through each resistor with the same magnitude. In other words, in a series circuit, current's always the same. That's the way that you define a series circuit. If the current is not the same in all components, then the circuit is not series. If it is, then the circuit is in series. Okay. The other one, draw a squiggly line here to separate the board, is parallel. Okay, so in a parallel circuit, we basically have resistors or loads that could be capacitors or inductors or other types of loads that are connected back to back. So obviously, just looking at the topology of this circuit right here, if this was resistor 1 and this was resistor 2, it would be obvious that the current wouldn't necessarily be the same in each resistor. For example, if we had a battery over here, and the battery, let's just say that the battery had an electromotive force or an electrical pressure of 10 volts, and let's say that this was 10 ohms for resistor 1 and this was 1 ohm for resistor 2, okay, the current that would be flowing in resistor 1 would not be the same as the current that would be flowing in resistor 2. And the way that we know that is by looking back at what we studied previously, Kirchhoff's voltage law. Kirchhoff's voltage law basically, in its abstract form, says that sum of the voltages around any closed loop has to be equal to 0. Okay, the more practical way to apply Kirchhoff's voltage law is to identify a closed loop. And would this be fair to say is a closed loop? Sure, this is a closed loop right here. Okay, and so since there's only two things in the closed loop, then this voltage would have to be equal to this voltage. So that's how we apply Kirchhoff's voltage law. So if this were 10 volts right here, then what would the voltage have to be right here? That would also have to be 10 volts. Okay? And so if we knew what the resistance was, then the current would be very easily calculated. The current would simply be equal to the voltage divided by the resistance. And that comes from Ohm's law. Okay? And so for this branch right here, this would be, let's say, current through resistor number 1. The current through resistor number 1 would be equal to 10 volts divided by 10 ohms, which would be equal to 1 amp. Okay? And then moving over to this portion of the circuit, it would be fair to say that this is a closed loop. Okay, it would also be fair to say that this outer loop is also a closed loop. So regardless of whether or not you use the inner closed loop or you use the outer closed loop, you're still going to get 10 volts across this resistor. And so let's see how we get that. If we use this outer loop right here, okay, we've only got two things in the loop. We've got the voltage source or the battery, and we've got the resistor. Okay, and so this voltage must be equal to this voltage. And so we know that there's 10 volts across that resistor. Kirchhoff's voltage law is that simple to apply. Okay, going back, when we calculated the current that was flowing through this resistor, we used Kirchhoff's voltage law to determine the voltage drop across resistor number 1. And we found that was 10 volts. So if we use this loop right here, it would also be the same application. In other words, this voltage would have to be equal to this voltage. So in parallel circuits, that's the reason that we wire up homes in a parallel configuration, is so that the voltage is the same everywhere. Like in your house, you have 120 volts in all your receptacles, and the reason is because we want everything to be running on the same voltage. Okay? So if we were to calculate the current that was flowing in resistor number 2, that would be equal to the voltage drop across resistor 2, which doesn't change because it's in parallel, divided by the resistance of that branch, which is 1 ohm. So it's 10 volts divided by 1 ohm, which is clearly 10 amps. So obviously, if we look at these currents, 1 amp and 10 amps, they're different. The current flowing through here is not the same as the current flowing through here. Okay? Whereas in a series circuit, the current flowing through each resistor has to be the same. In a parallel circuit, the current flowing through every load does not have to be the same. It could be, like in the case where both resistors had the same opposition to current flow or the same resistance, then the current would be the same, but that would be a special condition. That wouldn't be universal. Okay? The majority of the time, the currents are going to be different. Okay? Even if you have 2 hair dryers and they're made by the same manufacturer, and you buy them at the same store, they're probably going to draw a slightly different current. Okay? And the reason is because they're just not made identically. There's going to be some, hey Hans, there's going to be some irregularity in the manufacturing of the circuit. Okay, so a quick review on what we mean by a series circuit, what we mean by a parallel circuit, what happens with current in a series circuit, in that the current is the same in all components, and what we mean by Kirchhoff's voltage law in a parallel circuit. In other words, the voltage is the same. So I like to think of it in this way. In a series circuit, my current's always the same. My voltage is going to change, probably. Okay? In a parallel circuit, my voltage is always the same. Okay? My current is going to change, probably. Okay? Now, the topic being the current divider focuses our attention on the parallel configuration. Okay? Because we've kind of beat the series configuration to death. We've had a lot of review and study on the series circuit, and so we're going to be moving away from the series circuit. But what we're going to find is that we're not going to leave it entirely, because when we get to the more complicated circuits, there's going to be portions of the circuit that are going to be series connected. They're not going to be all parallel connected. So let's move over here to this section of the board, and let's talk about the current divider. Okay? The most common form of the current divider consists of the circuit that we just solved, which is a battery that's configured in parallel with 2 resistors. So you've got some kind of a voltage source, and we're just going to say that it's a battery for simplicity, and we're going to say that the magnitude of the voltage coming out of that battery is, let's say, 20 volts. And let's say that this is resistor number 1 and this is resistor number 2. Now, how many of you brought calculators? Great. Have your calculators ready, because I'm going to ask you to do some calculations so that we can make this interactive. Okay? The idea of the current divider is very simple. It's the same thing that would happen if you had a water system. Let's say for a moment, hypothetically, that rather than an electrical circuit, this represented a water system. So this is my water pump, okay? And this is, let's say, 2-inch PVC, or 2-inch water line, 2-inch copper line. Some kind of tubing, that we use to run water in our homes. So this is a 2-inch line, this is a 1-inch line, and this is a 1-inch line, okay? If the system is under a stable pressure, in other words, things aren't transient or changing, they're under a stable condition, okay? And this is a 2-inch pipe, and this is a 1-inch pipe, and this is a 1-inch pipe, then would it be fair to assume that the flow of water here would be the same as the flow of water here? Well, what I'm saying is that if this pipe is a 1-inch pipe, okay, then the diameter is going to define the opposition to the flow of water. Okay? If this is also a 1-inch pipe, then it's going to have the same opposition to the flow of water. Okay? So really the resistance or the opposition to the flow of water would be the same. Okay? So the condition that I'm describing here is a condition where if this is a 2-inch pipe, this is a 1-inch pipe, and this is a 1-inch pipe, first of all, the water flows down the main pipe, and then it divides off into the smaller pipes. Okay? The same thing happens in an electrical circuit. Current divides up. If you give it a place to go, it's going to go. Okay? It's always going to follow the path of least resistance. It's always going to follow the basic laws of the scientific model. Okay? But it's going to take the path of least resistance, and if you give it 2 places to flow, it's going to flow in 2 places. If you give it only 1 place to flow, if we come back to our series circuit, if you give the current, or let's say this was a water system, if you give it only 1 place to flow, then the current, or in the analogy of the water system, it's going to be the same everywhere. Okay? We're talking about a current divider, meaning that things are being divided up. You could think of, I'm dividing up money, right? I've got a certain amount of money, and you're getting 50%, and you're getting 50%. So that means, if I have $100, you get 50 of it, and you get 50 of it. If we have a circuit here, and let's just say that this resistance right here is 20 ohms, and let's say that this resistance right here is 200 ohms, okay, then just looking at this circuit right here, would I assume that the current is dividing equally in these 2 branches? No, I wouldn't assume that they'd be dividing equally, and the reason is because of the Ohm's law formula that says current is equal to voltage divided by resistance. Okay? So in branch number 1, and by the way, we call each one of these vertical legs branches. Okay? In branch number 1, we've got a resistance of 20. In branch number 2, we've got a resistance of 200. So if the resistance goes up, the current does what? The current goes down. So we'd assume that we would have a lower current flow in this branch, and we would have a higher current flow in this branch, right here. Okay? This right here, this circuit, this is the simplest example of what we refer to as a current divider. Okay? Now, we're going to be using this a lot throughout the course. We're going to be using it in a very simple form, and we're also going to see more complex examples of it. Okay, but the one thing that we know we can always do is we can boil it down to an equivalent circuit, meaning that the circuit has one source and one load. Okay? And when we do that, we can then calculate everything. Okay? Of course, it's not physically the same. In other words, if I were to take this circuit and convert it into one battery and one resistor, it's not physically the same circuit. Okay? But it's going to be electrically the same circuit. And so that's why we call it an equivalent circuit. We don't mean to imply that two resistors is the same as one. We mean to imply that there's a way to mathematically simplify the circuit. Okay? All right. So let's go ahead and do that, and then let's calculate the currents that are flowing in the circuit. Okay? So I'm going to move over here just slightly to the right. And what I'd like to do first is I would like to reduce this circuit. I'm going to erase my Ohm's law formula so I have a little more room. I would like to reduce this circuit into its simplest possible form, which is one battery and one resistor. Remember, all circuits can be reduced into one source and one load. Okay, when we get into AC circuits and we have inductive reactance, capacitive reactance, we're going to call this impedance instead of resistance. But it still means opposition to current flow. Okay? So all the stuff that we're learning now is going to apply to AC circuits. There's just going to be one more little complexity that we're going to have to deal with. Okay, so if this guy right here is the total resistance, or the equivalent resistance, which I like to call R1, 2, and that's just so that I can account for the resistors. In other words, I can look at this and I can say, oh yeah, I didn't forget and leave one of them out. You know, let's say I had 8 resistors, right? Then I'd write R1, R2, R3, all the way to R8, and that way I could be sure that I didn't leave one out. If I calculated what this equivalent resistance is, I would have to use the equivalent resistor formula, okay, which we've already studied. And so we're just going to do that. So go ahead and get your calculators out. The total resistance for a parallel circuit is equal to the inverse of 1 over R1 plus 1 over R2. That's the general form for a parallel circuit if you want to find the total equivalent resistance. So what we're going to do is we're just going to go ahead and erase these numbers, or these variables, and put numbers in for it. R1 has a value of 20 ohms, and R2 has a value of 200 ohms. Okay, now, before we even put anything into the calculator, what do we know that the total equivalent resistance must be less than? The lowest resistor. So if we come up with a total resistance of 27, we know we've done something wrong. So it's just kind of a cross and check thing. Okay? Okay, so I suggest, again, starting from the bottom, putting in 20, inverting it, hitting the plus sign, putting in 200, inverting it, hitting the equal sign, and then inverting that. And then you may have to hit the equal sign again. So if you do that, what do you get? 18.18?
Yeah.
Okay, 18.18 ohms. And then if we do our check, does it turn out that our total equivalent resistance is smaller than our smallest resistor? Yes. Okay, so we probably did it right. Okay, we can be confident that it makes sense. So then if I come back here and I erase my writing and I put that the total equivalent resistance is 18.18 ohms, and that the source voltage is equal to 20 volts. Okay? Other than the fact that there's a different number of components, is there any electrical difference between this circuit and this circuit? No. That's why they're called equivalent circuits. Okay? Now, when I have the circuit in this form right here, where I have only one voltage source and one resistor, is it fairly simple for me to calculate the current? Right, and what would I use? What theory or law? I'd use Ohm's law, right? Right, so by Ohm's law, if we want to be fancy about it, current is equal to voltage divided by total resistance, which in our case is equal to 20 volts divided by 18.18 ohms. So what do we get when we do that? So you put that in your calculator. 20 divided by 18.18. 1.1. Well, it's definitely gonna be bigger than 1, right? Because if it were 20 over 20, it would be 1. So, you want to check it again?
Yeah, it's
1.10. 1.1. Yeah. So 1.1, and what's the unit? Amps. Okay, so that is current flow. So the current that's flowing from this source out to this load is 1.1 amp. Now, because of the fact that these are equivalent circuits, as I've described, would it be fair to say that the current flowing here is 1.1 amps? Right. It's the whole idea of the equivalent circuit, okay? And reducing it down so that we can go back to the more complex circuit and we can put the current in there, okay? Now, once we know what the current is that's flowing here, okay, there's actually a couple of different ways that we can figure out how the current is dividing up, okay? One way is what I like to think of as the no-brainer way, or the simplest, or the most simplistic way, okay? And that is to realize that because this is a parallel circuit, and because Kirchhoff's voltage law always works, that the voltage here is the same here and is the same here. So if I know the voltage here and I know the resistance here, can I just use Ohm's law to calculate the current? Yeah. So we know that current is equal to voltage divided by resistance. So for the current that's flowing in branch 1, that's going to be equal to the voltage, which is 20 volts, divided by the resistance, which is 20 ohms. And that's going to be 1 amp. So we know that we have 1 amp flowing here. For the current that's flowing in this branch of the circuit right here, we're going to use the same formula, but a different subscript. The current flowing in branch number 2 is equal to the voltage across this branch. And is it going to be 20 volts? Of course, it's going to be 20 volts. And which law tells us that? Kirchhoff's voltage law. Right. Kirchhoff's voltage law tells us that. Okay, we know that this voltage right here is 20 volts by Kirchhoff's voltage law. Okay, and then of course the resistance of this branch is 200 ohms. So 20 divided by 200 would be 0.1, right? Okay? So this is equal to 0.1. Now, if we erase our equivalent circuit down here, which allowed us to calculate the total resistance and the current that was flowing. If we erase this circuit down here, what we can do is we can very simply calculate a few things that are very important and that we're going to use throughout the whole course. Okay? One of them is to verify Kirchhoff's current law. Remember we had Kirchhoff's voltage law? Kirchhoff's voltage law in its simplest form says that the voltage here is the same as the voltage here around this loop, but it's only good around the loop. If this is a loop right here, this is a loop, then the voltage here is the same as the voltage here. Okay, so we use Kirchhoff's voltage law to find voltages. We use Kirchhoff's current law to find what? Currents. Okay, so it's kind of like adding money with Kirchhoff's current law. In other words, it's just algebraic addition. And Kirchhoff's current law tells us, in other words, by Kirchhoff's current law, okay, that the current that's flowing from the battery, and our book likes to use I sub t for the total current, or the current that's coming out of the battery. The current coming out of the battery has got to be equal to the current going in here plus the current going in here, because there's no current going anywhere else. Okay? So Kirchhoff's current law says that the total current is equal to the current flowing in resistor 1 plus the current flowing in resistor 2. Okay? So if we try plugging those numbers in, we find that the total current is equal to the current flowing in resistor 1, which is 1 amp, plus the current flowing in resistor 2, which we found to be 0.1 amp. Let's go ahead and label this 0.1 amps. Okay, so this is plus 0.1 amps. So of course, when we add them together, we get 1.1 amps. And what we find is that when we compare that number to the number that we calculated using the equivalent circuit and Ohm's law, we get the same number. Okay? Let's do one that's very similar to this using a similar method, and then let's introduce the current divider formula, which we talked about very briefly, but people have some trouble with it, and it's not at all unusual to be found on aptitude exams for industry. Okay, so I want to make sure that we have a good handle on it. Let's come up with a completely different problem. And let's see that even if the problem gets a little bit more complex, we still do it the same way. Okay? So let's say that we have an or let's say that we have a lead acid battery, and let's say that that's hooked up to 2 resistors, but we're going to make the values that we have to put in the calculator for most of us. Okay, so the value of the battery we're going to say is 27 volts. Okay, so there's 27 volts being applied from the battery to the circuit. The value for resistor 1, let's say that that is 18 ohms. And the value for resistor 2, let's say that that is 7 ohms. Okay, so we don't have nice, easy, even numbers, but the method that we use to figure out what the current is in each branch, and thus the total current, is still the same. Okay, so would it be fair to say that we could use Kirchhoff's voltage law to figure out the voltage across this resistor and the voltage across this resistor? Yeah. And what would that voltage be? 27 volts. Right. It'd be 27 volts. And the voltage is the same because of the fact that we have a closed loop, right? And there's nowhere else for the voltage to go. In other words, you could think of it like the voltage being enclosed or encased or trapped in that loop, okay? And it's actually energy that's circulating around the wire, okay? That's why we talk about magnetic and electric fields. The magnetic field, you know, circles around the wire anytime that current flows through the wire. Anytime you have current flowing through a wire, you have a magnetic field around the wire. And then anytime you have an imbalance of charge, you have an electric field. Okay? So generally, when you have electric circuits, you have electric and magnetic fields present all the time. Okay. So let's just say that we wanted to immediately calculate the current that's flowing in branch number 1 right here. Well, if we know that by Ohm's law it's voltage over resistance, then we know that the voltage on this resistor is what? 27, because this is a closed loop. So this voltage has to be equal to this voltage. So this is 27 volts, and that's going to be divided by 18 ohms. So somebody with their calculator, tell me what they get when they divide 27 by 18. Is that what we get, 1.5? So we got 1.5 amps. So we'll go ahead and just write that here. We've got 1.5 amps flowing into that branch. Okay? And then likewise, we've got a closed loop on the very outside, don't we? We also have a closed loop on the very inside. And they both tell us that the voltage here is what? 27 volts. Okay? So if we want to calculate the current flowing in resistor 2, that's equal to the voltage drop across resistor 2. So that's the voltage drop across resistor 2 divided by resistor 2. So that's simply equal to 27 volts divided by 7 ohms. So when you put that in your calculator, what's 27 divided by 7? 3.85 amps. So this is 3.85 amps. Okay? And so we'll indicate that with an arrow here and say this is 3.85 amps. Now, Kirchhoff's current law tells us what? It tells us that the current that's leaving the battery must add up to the current that's flowing off into all the branches. If we have 2 branches, then it's only flowing in 2 places. If we've got 18 branches, then it's flowing in 18 places. Okay? But for us, Kirchhoff's current law can be written this way. The total current, which is the current that's flowing out of the battery, that's the total current. The total current is equal to the current that's flowing into resistor number 1 plus the current that's flowing into resistor number 2. Okay, does that account for all our currents? That accounts for all our currents. Okay, and so if we add those together, then we get 1.5 plus 3.85. And this is all in amps. So what do we get for our total current? 5.35? 5.35. 5.35 amps. So the current flowing here then is 5.35 0.35. So as you can see, using the current divider, you can figure out where the currents are everywhere in the whole circuit. Okay, now, let's assume for a moment that we have a circuit and all we're asked for, we're taking an aptitude exam for Chevron or PG&E or some large company. And in the aptitude exam, what they're asking us for is the current that's flowing through one resistor and one resistor only. Okay? And this is something that's very common. You're going to see this on the exams here. You're going to see it on the midterm and the final for the distance learning class. You're also going to see it on industry aptitude exams. Okay? And so let's make sure that we learn it. So we're going to take the information that we know to be true about this circuit and we're going to leave it alone. We'll erase our calculations because we've already done them. Okay? And what we're going to do is we're going to redraw this circuit. So we've got a battery, we've got a resistor, and we've got another resistor. So this is our total voltage. And let's just say that for the sake of an industry aptitude exam, they don't tell us what this is. This is a big question mark. This is very common that I do this to you. And I'll do it to you to get you ready. Okay? They won't tell you what the current is or what the voltage is here. Okay? But what they will do is they will tell you what the resistance is for resistor 1. So resistor 1, they'll tell you that guy's 18 ohms. And for resistor 2, they'll tell you that guy is 7 ohms. Okay? So they'll give you that information. And then the other piece of information that they'll give you is the current that's flowing out of the battery. So the current that's flowing out of the battery into the rest of the circuit is 5.35 amps. That's what they'll give you. And then what they'll ask you for is, what is the current flowing in resistor 2? That's all they want to know. Okay? Now, obviously, if we knew the voltage, okay, and we're making this problem up from a problem where we do know the voltage, but we're pretending like we don't know the voltage for the sake of learning the current divider formula. If we knew the voltage, then we can immediately go to Kirchhoff's voltage law and say that the voltage here would be the same as the voltage here, and then we could use Ohm's law to figure out what this current is, right? But if they don't give us the voltage here, we don't have the luxury of being able to say that the voltage here is 27 volts or 25 volts or whatever it is, because we don't know. We don't know what it is, okay? But the one thing that they have given us is the current that's being drawn from the source. Now, the reason that they do this to you when they give you aptitude exams is because it's very common when you're checking up a load panel to go and to check how much current is being drawn from the panel. And then to go to each one of the motors or the robotic systems or the computer numerical control systems or the server banks or whatever the loads are, and to check those to see how much current is being drawn by those. Okay? Sometimes it's done for energy efficiency audits. Sometimes it's done just to make sure that you don't have loads that you're not aware of. Sometimes it's done to make sure that your neighbor isn't stealing power from you. There have been many instances where you'll have, a common wall between two companies that are, making, bearings or toilet paper rolls or whatever the case may be, okay? And there may be some way for somebody on a weekend, to access the one space, through an attic, where they can run a piece of conduit up and they can hide it, so that unless somebody actually crawls up there, they won't actually see the conduit up there. So during the weekend, they can have somebody that can sneak over, and they can go and they can tap into your breaker live using high voltage gloves. They tap into your breaker, behind the part of the breaker that you open. So unless you're doing some kind of an inspection, preventative maintenance inspection, you're never going to see it. Okay? And so they'll run the wire back there, and they'll run the wire over and through the rafters or up in the attic area, and you won't be able to see it. You walk around, you do a visual inspection, and it's like, okay, where are all the loads? Oh, well, there's a lathe over there, and there's a server bank over there, and there's a CNC milling machine over there, and there's 15 motors over here that are, running this process, and there's a big pump over here, and that's all. And so then you'll, get a table, and you'll fill them all out, and you'll go around with the clamp on meters, and you'll check all the currents. And then when you go back to the panel, you'll check the current that's being drawn from the panel. And then by using Kirchhoff's current law, you'll find out that the total current being drawn from the panel doesn't add up to all the currents that are being used by your facility. Why? The reason is because some of the current is being stolen, and it's driving a whole bunch of load next door, and so, that company obviously is not paying for it, and, they're stealing, and it happens a lot. And it's not an everyday occurrence, but it's something that, having worked for the power utility for close to 15 years, it's a problem. It's a big enough problem that we have two groups that'll range anywhere from 7 to 15 people per group that do nothing but energy theft investigation. And so they do it for companies as a courtesy to them, and they'll also do it for the power company, because sometimes people think that they can steal from the power company by going around the meters, stuff like that. And so it's this right here has a very practical application, because what is it tied to? It's tied to money, right? If you don't know Kirchhoff's current law, and they put you in charge of figuring out whether or not somebody's stealing energy from your panel, stealing current, right? You're never going to be able to figure it out because you don't know Kirchhoff's current law, okay? But it's simple to figure out if you know it, and it's not hard to learn. Okay, so let me erase the dollar sign. And let's say now that in this particular circuit right here, we had this information. In other words, we put a clamp on meter, okay? And let me step down and just grab a clamp on meter just for a little effect here. In the utility companies, pretty much everybody's issued one that works in the field. And they look like this. A lot of different companies make them, but Fluke is a real popular manufacturer of these meters, right? And so basically, if you have a piece of wire, and let's say that this pin was, a piece of wire, right? So you got this piece of wire running, then all you have to do is just open the clamp, put it around the piece of wire, okay? And then of course you'd have to turn it on. So you'd turn it on to whatever you were measuring. Like if you were measuring DC or AC current, you'd turn it to AC current. And then you can see right there, it's telling us there's no current flowing in through the hole. We call this a Hall effect current meter, okay, because it uses a process in physics that was discovered by a guy named Hall, okay. But it's extremely useful and extremely safe, because if you're trying to measure the current that's flowing through a wire, okay, and you've got a glove on that's rated for 1,000 volts. In other words, you could go up to a wire that was bare, and you could be standing in water, which I wouldn't recommend, but you could be standing in water, and you could grab on to that energized wire, and theoretically, it wouldn't affect you. It would be no different than me standing here holding on to this pin, okay? So that's the thing that's so nice about these clamp-on meters, is that you don't have to break a connection, you don't have to hook up a meter. All you have to do is open up this clamp and clamp it around the wire, and then it tells you how much current is flowing. So if you're doing an energy survey, you go around and you check the current that's flowing to the servers, you check the current that's flowing to the water pumps, you check the current that's flowing to the lathes, and then you add all those numbers up using Kirchhoff's current law. So a device like this is used in conjunction with Kirchhoff's current law, and then you get the total current that you should expect to be flowing from your main breaker panel. Then you go to your main breaker panel and you check the big fat wire coming out of your main breaker panel, and you see how much current is flowing out of it, and that current had better add up to all the currents that you measured throughout your plant, okay? If it turns out that there's a discrepancy, you know, that's more than a couple of percent, and there may be a little error in the meter or something, but if there's a discrepancy that's more than a couple of percent, then you've either forgotten a load that's in your building somewhere, or somebody's stealing energy from you, okay? And, you know, trust me, you know, you can be the hero of the day, and, you know, this can result in a future promotion. If you're the guy that takes on their own initiative, you know, the job of going around and doing a survey to make sure that everything's balanced and that all the power that you're paying for is power that you're using, okay? Because it happens a lot. Okay, now, there's a formula that I'm going to want you to have on your crib sheets, which you're going to use in industry, which is called the current divider formula. And this current divider formula is in your book, and this is what it looks like. It says that the current that's flowing in the branch you care about. So here's one branch, here's another branch. Okay? You may care about this one and not care about this one, or vice versa. All that X means is, you know, 1 or 2, whichever one you care about. Okay, that's equal to the total resistance, the total parallel resistance of those 2 resistors divided by the resistor in the branch you care about. So R total R over R sub X. Multiplied by what? The current coming from your battery or from your source of power. So in our particular case, in our particular problem, what is the total parallel resistance? Did we figure that out? Yeah. For this one? It's 10.8. So our total we found was equal to 10.8 ohms. No, that can't be right, because it's got to be smaller than your smallest resistor, right? So let's fix that. See, that's the nice thing about having those little rules, because if you have written something down in error, then you can figure it out. So our total is equal to the inverse of 1 over 18 plus 1 over 7. So what is that? 5.04. 5.04 ohms. Okay? And we see that that is in fact smaller than the smallest resistor. Okay? So our total is 5.04. What is R sub x? If we're interested in the current that's flowing here. 7 ohms. And then what is the total current? 5.35. So this is simply equal to the total resistance, which is 5.04 ohms, divided by the resistance of branch number 2, which is 7 ohms, multiplied by the current that's coming out of the battery, which is 5.35 amps. Okay? Now, when you calculate that, it's going to turn out that you're going to get 3.85 amps. Same current we got there. Okay? Verify that for me. Is that correct? Did anybody put in their calculator? Okay. We're just taking my word for it here?
No, that's good.
Okay, all right. Okay, so this is the current divider formula, and I'm going to write down this name of it down here. Current divider formula. That's this guy right here. That's this. Well, I'll put a squiggly box around it. That's that formula right there. If you know the current that's flowing out of your main panel, and you know the resistances of your loads, you can use the current divider formula to go directly to one of your branches and figure out what the current should be flowing there without knowing any voltages. Okay? Questions? Okay. Or what about, we're down to 2? Are we? Okay. All right, very good. Make sure that you take a close look at this current divider formula because you will need to know it. And everybody drive safely. Okay? Good night.